So moving on. Where do we use these MAC addresses? Going back to the protocol data unit that I was speaking of earlier, the protocol data unit is simply the way the data is structured at layer 2, at the data link layer. So, the protocol data unit at layer 2 is called a frame. Now, what does this frame look like? Let's find out. So, I'm just going to draw a box. And I'm going to draw this with a word of warning. I'm only going to put the fields in this frame that are pertinent to the CCNA class. There are other fields inside of this frame, but you guys don't need to know it till you get to your CCNPs. So, you will have your destination, and I'm going to abbreviate it to DEST, MAC, your destination MAC address, which would be the MAC address of the device you are transmitting to, or the person you are sending the letter to, your source, MAC, your actual data. So you can think of, and I've left this field empty for a second on purpose, but you can think of the frame as your envelope and your data as the actual letter that you're sending. The last field here is called your frame check sequence. So FCS stands for frame check sequence. This field houses what is called the CRC, or the cyclic redundancy check. Now, in some books, you won't even see the last field say FCS. It'll just say CRC, standing for the cyclic redundancy check. But in actuality, the last field is called the frame check sequence, and it houses the cyclic redundancy check. Now, what is the cyclic redundancy check? Before the transmitting device transmits the frame, it performs a calculation. There is an algorithm that is sitting inside the frame check sequence called the cyclic redundancy check, and the CRC performs a calculation on the whole frame, and it comes up with a number. It yields a number. So let's say the calculation was performed, and the number it came up with was the number, let's say, 15. The number 15 is put inside of the frame check sequence, and the frame is transmitted. The receiving device receives the frame and then performs the same calculation on the frame and comes up with its own number. So let's say the number the receiving end came up with was also 15. Then the receiving device matches or compares its own yield of the calculation, or the number itself came up with the number already residing in the frame check sequence. If the two numbers match, the frame was not corrupted in transit. So if the two numbers match, it means the frame went through and there was no data corruption, and the frame is accepted. Now, if the numbers don't match, let's say the receiving end got the frame and did the calculation and came up with the number 20, that's a sure shot way of telling that the frame was corrupted in transit and the frame is discarded. The receiving end does not accept the frame, it just drops the frame. Now, you see in the frame, in the diagram for the frame, I have said that the destination MAC address comes first before the source MAC address. As we learned that the MAC address is 48 bits in length. Now, if the source MAC came first and the destination MAC came second, the receiving end would receive the frame, would have to read 48 bits worth of useless information to it before trying to compare its own MAC address with the MAC address residing in the destination MAC portion of the frame. So the destination MAC portion of the frame comes first by design. So as soon as the receiving end gets the frame, it can immediately start comparing, doing a bit-by-bit comparison with its own MAC address and the destination MAC address in the frame. And if it matches, it accepts the frame and says that, okay, this frame was meant for me, barring a fail in the CRC. If the CRC fails, of course, the frame is dropped, but the first check the device will perform is match the destination MAC address residing in the frame with its own MAC. That's why this field comes first. Up until now, I have mentioned what type of addressing is used at layer 2, or the data link layer, and what the protocol data unit is at the data link layer. The protocol data unit being the frame. I haven't mentioned yet what devices work at the data link layer. And there's only one device specifically. Well, other devices also work at the data link layer, but most specifically, a switch operates at the data link layer. Now I'm going to explain how a switch functions. So I'm going to go ahead and draw a rudimentary switch on the board. Excuse my drawing skills. Let's say this is switch 1. And to it are connected 4 devices. Let's say PC1, PC2, PC3, and PC4. Now, just for example's sake, can we just pretend that PC1's MAC address is A. PC3's MAC address is C. And I'm well aware of the fact that these are only 4 hex characters per MAC address, which makes for 16 bits, but please don't make me write out 48 bits worth of A's. So we're going to stick to 16 bits and pretend this is 48 bits. And PC2 is B, and PC4 is, let's go with D. Also, we're going to pretend that PC1 is connected to switch 1 on port, we're going to call it port P1. PC2 is connected on port P2, PC3 P3, and PC4 P4. Now, inside of a switch, in software, there exists a table called a MAC address table. So let me go ahead and draw a MAC address table out too. So this is going to be your MAC table. I just skipped the word address because I didn't think I'd have enough space, but this is called your MAC address table. The MAC address table is a listing of all ports on the switch. So port 1, port 2, port 3, port 4, and other ports if the switch has them. But right now we're just dealing with port 1, 2, 3, and 4. And the MAC addresses of the devices that are connected at the other end of the port. So once this operation is done, what you're going to have in front of P1 is AAAA. So the MAC address table has a listing of all the ports available on the switch and the MAC addresses of the devices that are connected at the other end of that port. So when a switch is brand new and devices just get connected and the switch is powered up for the first time, this MAC address table is empty. This MAC address table is completely empty. Now let's pretend that PC1 transmits a frame to PC4. So PC1 transmits a frame, and the source MAC address in that frame is AAAA, and the destination MAC address in that frame is DDDD. And it's transmitting some data which does not concern us. That frame gets to switch 1, port 1. Now remember, at this point, port 1 in the MAC address table has nothing in front of it. As soon as switch 1 receives the frame from PC1 inbound on port 1, switch 1 reads the source MAC address field in the frame and adds PC1's MAC address to the MAC table. So A gets added to the MAC table. As soon as switch 1 reads the source MAC address field in the frame, it adds the source MAC address to the MAC address table in front of the port that received the frame. Switches learn or populate their MAC address tables looking only at the source MAC address field in the frame. Once again, a switch learns MAC addresses by looking at the source MAC address field in the frame. So, PC1 transmits the frame, switch 1 gets it, switch 1 learns PC1's MAC and adds it to the MAC address table in front of port 1. Then switch 1 looks at the destination MAC address in the frame, which is DDDD, and then tries to find that destination MAC address in its MAC address table. And the rest of the MAC address table is empty. So, switches make their forwarding decision, where to forward the frame once it receives it, based on the destination MAC address field in the frame. Once again, switches make their forwarding decision based on the destination MAC address in the frame. So since the switch does not find the destination MAC address in the MAC address table, switch 1 floods the frame out, all the ports except the port that originated the signal in the first place, which was port 1. So the frame gets flooded out to port 2 to PC2, out port 4 to PC4, and out port 3 to PC3. All of the devices get the frame. Now, what does PC2 do with the frame? The PC2 looks at the destination MAC address in the frame, the destination MAC address field of the frame, and compares the MAC address sitting in the destination MAC address field with its own MAC address. So the destination MAC address field in the frame at this point says DDDD. It does a comparison against its own MAC address, which is BBBB. Doesn't match. PC2 drops the frame. Same with PC3. DDDD, which is the MAC address in the destination portion of the frame, does not match CCCC, so PC3 will drop the frame. In case of PC4, the destination MAC address field matches PC4's MAC address. So PC4 will accept the frame. Now, if at some later point, PC4 replies back to PC1. So PC4 replies back to PC1. When that frame arrives on port 4, switch 1 will once again read the source MAC address field in the frame, because switches learn or populate their MAC address tables looking at the source MAC address field in the frame. The switch 1 will add the MAC address DDDD to the MAC address table. Then switch 1 will try to find the destination MAC address, which is AAAA in the frame, in the MAC address table, and it finds it. AAA is available on port 1. So switch 1 in this case will not flood. Remember, switches forward frames or make their forwarding decision looking at the destination MAC address field in the frame. Switch 1 will find AAAA on port 1 and forward the frame out directly to PC1. So at some later time, when PC3 and PC2 communicate, or somebody communicates with these two PCs and they reply back, the MAC address table will get fully populated, and port 2 will have BBBB in front of it, and port 3 will have the entry CCCC. Once the MAC address table is fully populated, there will be no flooding behavior occurring. The whole point of the flooding behavior is that I don't know where this frame is going. I don't know the destination, which means the destination MAC address in the frame does not exist in my MAC address table. So I flood it out everywhere in attempts to find where this device is located. Once I learn where all the devices are located, then the forwarding decision between PCs will happen immediately. As soon as PC1 transmits, let's say, to PC3, switch 1 will look up CCCC in its MAC address table and forward that frame out port 3. One of the mistakes I see people make, even though they say that they know the operation of a switch, and by now you should have a pretty firm grasp of how a switch operates, they confuse the word flood with the broadcast. I use the word, when host A or PC A, whenever I use the word host, it's synonymous with the PC. When PC1 transmitted the frame the first time, when the MAC address table was unpopulated, there was nothing in there, I used the word flood. I said the switch floods out the frame to all the other devices except the port that originated the signal. Sometimes I see people use the word broadcast. No, no, no. That will get you in an interview process, at least if I'm interviewing you. So, a broadcast frame is a frame that has all Fs in the destination portion of the frame. I'm going to go ahead and draw that out for you, so we never get this wrong again. So this is my destination MAC. So the destination MAC for a broadcast frame is going to be all Fs. Source MAC can be whatever, and then the data, and then I'm just going to put CRC over here. Of course, the field itself is called frame check sequence. So a broadcast frame is a frame that has all Fs, or all ones, actually. In binary, this equates to all ones. So a broadcast frame is a frame that has all Fs in the destination portion, in the destination MAC address portion of the frame. That frame that PC1 sent to PC2, the source MAC address in that frame was AAAA. The destination MAC address in that frame was DDDD. That was a unicast frame. And just as a quick review, just in case some of the people listening to this do not know this, a unicast is a one-to-one transmission. So PC1 to PC4 transmission. A broadcast is a one-to-everybody transmission. So if PC1 sends out a broadcast, PC2, 3, and 4 will receive the frame. The end result is just like a flooding behavior, but you can't call it a broadcast because it's not a broadcast frame. It is still a unicast frame, which is a one-to-one transmission from PC1 to PC4. Source address is AAAA. The destination address is DDDD, not all Fs. So that is a unicast frame. The flooding procedure is only done to find devices when the switch does not know where they're located, or their MAC addresses are not in the switch's MAC address table. A broadcast is sent to everybody on purpose. So once again, a broadcast frame will have all Fs in the destination portion of the address. A unicast frame will have a source MAC and a destination MAC. Now, what is the end result of a broadcast frame being received by a switch? Of course, it is sent out all ports except the port that originated the signal. Now, why is it sent out all ports? Because this address will never exist in the MAC address table. The MAC address table, for the most part, barring some stuff that you might learn in CCNP, for the most part, only holds unicast addresses. So since this address will never exist in the MAC address table, as soon as a switch receives a frame with all Fs in the destination portion of the frame, the switch will send it out all ports. And I'm refraining from calling it a flood. It's not a flood. The flooding behavior has a different purpose. That is a broadcast. Okay, hopefully we have that cleared out.